Let us start this lecture with a thought process by Albert Einstein, a genius in modern centuries. Any intelligent fool can make things bigger and more complex. It takes a touch of genius and a lot of courage to move in the opposite direction. Let us recall what we learned in the last lecture. In the last lecture, we looked at the effect of spinning or acceleration due to spinning and also the particle size of ammonium perchlorate or any oxidizer in case of composite propellant. Or in other words, if you remember that the effect of acceleration on the burning rate is also influenced by the composition of the propellant. We could get as large as something 2.5 times, and also this is might be occurring whenever the rocket engine will be spinning for its own stability in case of missile application or other applications. And later on we also looked at how does it affect the thrust time curve, and the acceleration will be changing with respect to time when the propellant regresses. In other words, the propellant port or the port of the grain increases size with consumption of the propellant. Later on also we looked at particle size, which plays an important role, and the smaller the particle size, the larger will be the burning rate of the propellant. And so also the temperature, like when the temperature of the propellant increases, the burning rate also increases, that we had seen in the last lecture. And towards the end we basically looked at the effect of the erosive burning. Erosive burning can occur only in the beginning, particularly when length of the propellant grain will be much higher. And today also we will discuss more about the erosive burning. Let us look at a side burning grain, and having certain length of the grain. This is your length of the grain if you look at, and as we have seen that when the propellant surface regresses, then the mass will be added to this port of the propellant grain where the combustion will be taking place, and the mass goes on adding. As the mass is added to this thing, both from the top surface and the bottom surface, both the surfaces, then the mass will be increasing and the port area is same. So, if you look at, this is the constant port area, this is your port area AP, and as the port area is constant, therefore, the velocity will be increasing, and beside this there will be a boundary layer from both the surface which will be growing, and hence there will be increase in the velocity, and that velocity will be really much higher towards the aft end. This is your aft end and this is your front end. So, as a result there will be turbulent flow, and that will enhance the mixing, and then propellant will be basically regressing at a higher burning rate towards the aft end. And keep in mind that in order to avoid that thing, what you will have to do is that you will have to either decrease the length of the propellant grain, or you will have to use the higher port area as compared to the throat area. And of course, there is a several other ways of also reducing the erosive burning, and which will be occurring in the very beginning of the combustion. And keep in mind that one has to design it properly, otherwise there will be problem. As it regresses, as the burning rate increases along with the length of the propellant grain, then what will happen? It will be regressing at a faster in this rate. So, there might be situation which will be coming such that towards the aft end of the burner will be all the propellant will be burnt out, and this such that the wall of the combustion chamber will be exposed to the high temperature and high pressure gas, and then it may subject it to failure. In order to overcome that problem, one can design the propellant grain in a tapered manner such that area of the port will be increasing along with the length of the burner, so that it will be compensated the increase in mass burning rate or mass addition due to burning of propellant along with the length. So, such that the velocity will be remaining constant and it will not go beyond the threshold level of the velocity at which erosive burning will be occurring. So, that is another way of designing the side burning grain in such a way that erosive burning can be avoided. And let us look at also the what will happen to the thrust or the chamber pressure, because chamber pressure will be detecting the thrust when it is expanded in the same nozzle for the same pressure ratio. So, if you look at the thrust law that is being plotted without erosive burning, that is this dashed line, and you can see that whenever erosive burning is there, there will be increase in the thrust, and of course, the time duration for which the complete burnt out of the propellant will be taking place is reduced as compared to no erosive burning or without erosive burning. A question arises, why it is so? I have already explained that there will be addition of the burning mass flow rate for the same throat area AT. So, that what will happen if it is choked, then the mass flow rate will be accumulated and there will be increase in chamber pressure. If there is a increase in chamber pressure, that can lead to the increase in the thrust, and so there will be initial increase of thrust whenever the erosive burning will be occurring. As a result, the more mass of the propellant will be consumed in the beginning, and then when this mass will be consumed and thrust will be there, then after that erosive burning will not be there, because already the port area is much higher as compared to the throat I mean like that ratio which is required, and the velocity will be reduced in the combustion chamber or in the port of the propellant grain. So, then that will be coming down, and when it is coming down, then it will be really coming to the actual one. In other words, when the AP or the port area increases without increase in burning area, then Vg is reduced. This is the gas velocity which will be going here Vg. Vg will be reduced, thus burning rate diminishes to the normal one. As the more propellant is being burned in the very beginning, therefore, the propellant entire propellant gets consumed little less time, within less time as compared to the original one. So, let us look at effect of gas velocity in a perforation or the grain cavity on the erosive burning or augmentation ratio. So, we look at some experimental data. So, this is plotted basically the erosive burning augmentation ratio, that is R by R dot. We use basically E B or the initial, that is this symbol we use R E B divided by R dot. So, this is same as R by R dot versus the free stream velocity, or we call it as a gas velocity V g. And you can see that the data is plotted for two cases. One is formulation I V, that is A P 72%, S T P V 26%, and ferric oxide is 2%, which will be basically have a higher additives, and the particle size of the A P is 20 micron. The burning rate is 1.265 centimeter per second, and this Fe2O3 is basically burning rate enhancers. And you can see that this is corresponding to that, the erosive burning ratio is increasing with the gas velocity. But if you look at the similar formulation, only difference is that the ferric oxide is not there. So, the burning rate is almost half or around that of this the earlier formulation. Then you will find that erosive burning rate is increasing, and this is corresponding to the chamber pressure of 4.2 megapascal and temperature of the flame is 2250 Kelvin. Of course, all these are measured at x 9 centimeter from the front end. You can see that the similar trend is occurring, only difference is that the change in this erosive burning ratio or augmentation ratio is much higher. Earlier it was very small, even at 300 meter per second, and maybe something 1.1 kind of things, but now it is 1.4, little bit more than that, and it is increasing. And it can be noted that whenever the regression rate is smaller, the effect of erosive burning on the burning rate is much higher. In other words, the erosive burning augmentation ratio will be higher, and this is very interesting result. One has to look at it and then keep while designing the thing. So, the erosive augmentation ratio up to 3 times can be really observed in some motor design. Therefore, it is very essential to take care of the erosive burning while designing a rocket engine, and it must be avoided. If it cannot be avoided, at least it can be minimized. Let us look at effect of propellant temperature on the burning rate, and it is very important to look at this aspect because of fact that it may affect the performance of the rocket engine. As we know that R dot, that is the burning rate, is equal to A P C power to the n, and we know A is nothing but A constant divided by T I. T I is your self ignition temperature and T P is the propellant temperature. And therefore, this propellant temperature T P is a very important parameter, because if it is increases, this difference will be reduced. As a result, that R dot will be increasing. But we need to look at what is the sensitivity of burning rate with respect to temperature at constant pressure, because if the temperature increases, the burning rate increases, and so also the chamber pressure will be increasing. And as I told in the last lecture, the mass will be accumulated and then it may increase the chamber pressure. If chamber pressure increases, burning rate increases. Therefore, we need to keep this chamber pressure constant and then look at it. By definition, that will be the sigma r, the sensitivity of burning rate with T p, that is this is nothing but this one, the sensitivity of burning rate and that is equal to rate of change of regression rate with respect to change in temperature and per unit burning rate when the chamber pressure is constant. So, if you look at that will be basically sigma r dot is 1 by r dot and d r dot by d T p where chamber pressure is constant, and what we will be doing, we will be basically putting this r dot into A P C in that, and pressure will take it out and then differentiate it. So, that this will be P C power to the n, and in place of r dot we are we can use this one, this is nothing but your r dot and dA by dT. And dA we know that A is basically A T I minus T p. So, therefore, we can get dA by dT p is nothing but your dA T I minus T p minus 1 divided by dT p, and that will be A minus then minus 1 then T I minus T p minus 2, and that will be basically A divided by T I minus T p power to the square, and this is we know this will be cancel it out basically, and this A is nothing but your A T I by T p. So, if you look at this will cancel it out and A is cancel it out. So, you will get is equal to 1 minus T I by T p. Keep in mind that sensitivity is a very burning rate with respect to propellant temperature is important, and if the T p is very close to T I, when T p is very closer to T I, then sigma r dot will be going to the infinity or very high values. So, therefore, one has to be very careful and while doing that. So, at chamber pressure of 7 megapascal, these values of sigma r will be around something 5 into 10 power to minus 3 degree Celsius inverse for, and this is for double base propellant. For composite propellant, this sigma r is something 3 into 10 power to minus 3 degrees Celsius inverse, and of course, this unit you know like it will be, you can say that 1 by degree Celsius or Kelvin, whatever is you are using. So, that does not matter because the difference is there. So, keep in mind that the double base propellant is more sensitive as compared to the composite propellant. Of course, when you add HMX to that, and that become little this thing lower, that is 2 into 10 power to minus 3. So, therefore, one has to be carefully using that. Generally, this sensitivity of burning rate with T p can be determined from the stand burner data, and by knowing this parameter of sensitivity of burning rate, one can really determine the regression rate provided you know certain data at of the burning rate at certain temperature. So, from this expression equation 1, then from equation 1 we can get d r dot by r dot is equal to sigma r dot into r dot dt. I can write down d just to so that if I will integrate this expression from T naught in a certain temperature at which we know the burning rate, then T I will get basically ln r dot by r naught is equal to sigma r dot t minus t naught. So, we can get basically r dot is equal to r naught e power to the sigma r dot t minus t naught. So, this is the expression what you will get, and keep in mind that if I know this r dot and if I know this T naught and we want to find out what will be r dot at certain temperature T, then I can very easily get by using this expression, provided that we know that sigma r dot. Let us look at the thermal model for solid propellant burning, and we have already discussed various kinds of flame for double base propellant and composite propellant. And in today we will be looking at the basically a model by which we can determine the burning rate of a propellant, and we will be considering only a single flame is standing off at certain distance from the regression surface. For example, like if we take this propellant and if this flame is standing at certain distance from this regression surface, and this is your regression surface, or I can call it burning surface. And here we are considering only single flame. There is no multiple flame like 3 flames in case of composite propellant, or the various flame zones in case of double base propellant. And here we are assuming that a steady state and one dimensional combustion which is taking place, and there is a temperature profile which is having, that means this flame is having T f, that is flame temperature. This is basically flame temperature, and this is T s is your surface temperature, and this is same as T p, that is propellant temperature. And we are assuming one dimensional flame and the temperature profile also one dimensional nature, but we have seen it is not true in both the double base and the composite propellant, but simplicity we have done. Our main objective of this model is to basically find out a relationship for burning rate or the regression rate, and we are assuming the process to be steady. So, under the steady state condition, we will be carrying out a energy balance at this surface, at the burning surface itself. So, by carrying out energy balance at burning surface, of propellant, we can have Kg, because and we are assuming only the conduction which is playing a role, that means the heat is conducted from this flame to that to the surface, Kg dt by dx, and this is your x direction what we are considering from the regression surface at is equal to, and this is the this side positive side, and there will be negative side also. So, and is equal to, and this heat which will be transferred due to conduction from the flame surface to the burning surface is basically to raise this, let us say there is a small amount of which is going, raising this temperature from unburnt temperature to surface temperature, and also that this portion will be now converted into the gas itself. So, there will be heat of phase change from solid to the gas. So, therefore, that has to be taken care, and that is equal to rho p r dot into C. This is your specific heat of the solid propellant into T s is your surface temperature minus U, this is your propellant temperature, plus delta H V, and this is your basically the heat of phase change from solid to the gas. And we know that rho p r dot is the product of propellant density, this is your propellant density, and burning rate r dot. And the other quantities, as I told earlier, that delta H V is the heat of phase of change from solid to gas, Kg is your thermal conductivity of the gas, because this side is your gas, and C is the specific heat of propellant, Tu is the unburnt temperature propellant. And keep in mind that how we will determine by dT by dx, that is the temperature gradient, and if you look at this is not a linear, but however, we will be assuming the profile to be linear, that means this is a linear temperature profile. We are assuming a linear temperature profile between this flame and the surface which we are considering. So, I can really find out that dT by dx is nothing but your flame, this is your flame temperature Tf minus Ts, this is the thing, and divided by the delta F is the flame thickness, you can say, is equal to Tf minus Ts x, and this is your standoff distance. In other words, what I am saying is that as delta F we are assuming as x star. And of course, this is a very crude approximation, and if you want to get this gradient, you will have to solve the gas phase conduction equation and the heat release, and then it will be very nonlinear in nature, and also the amount of convection will be there. So, those things has to be considered. We are not really going to do that. And what we will do now, we will have to use this one dimensional flame, particularly premix flame, and find out that this will be basically x dash, I can say, from thermal theory of one dimensional premix flame we can get x star is equal to delta F is equal to root over Kg by Cpg m dot. Kg is the conductivity of gas and Cpg is the specific heat of the gaseous product, and m is the mass burning rate per unit volume. And we know that mass burning rate, the average reaction rate, average mass burning rate due to chemical reactions gas phase chemical reaction is equal to basically A f YF N1 Y oxidizer N2 PM e power to the RUT. Keep in mind that YF is the mass fraction of fuel, Y oxidizer is mass fraction of oxidizer, and E is your activation energy, and RU is your universal gas constant, T is your temperature, AF is your pre-exponential factor. And if you know these things, and N1, N2 are the coefficient of that, and M is a pressure index or the coefficient of pressure. So, if you look at that, then we can really use it. So, if I say this is your equation 1 and this is your equation 2 and this is your equation basically 3 and this I can say 4. I can combine this thing, I can get basically by using equation 1, we can get R dot is equal to Kg dt by dx divided by C T s minus T naught plus delta H v into rho p, and keep in mind that we can write down that as Kg. In this place of this I can write down df minus Ts into this delta f I can write down, that is basically root over of Kg and root over of Cp into AF YF N1 YF N2 PM and E by RUT, and divided by the rho p C T s minus T naught plus delta H v. So, this Kg will be cancel it out, and this will be, and this became root over Kg. This is basically Cpg, this will be Cpg gas, just to distinguish that other one, other Cp. And so, you can get an expression, we can write down, this is basically R dot is equal to root over Kg Cpg AF YF N1 Y oxidizer, this will be oxidizer N2 PM E by RUT divided by rho p C T s minus T naught plus delta H b, that is T f minus T s So, let us look at what are the parameters that govern the regression rate from this expression, that is R dot basically increases when T f increases, and T s also, like when the T s will be decreasing, then R dot also increases. and R dot also increases when T p also increases, because what will happen, this is T u, this is nothing but your T p. So, if T p basically increases, this term is a smaller one, T s minus T u or T p. When it is smaller, then R dot also increases, and R dot also increases when X star or the flame length decreases, and when this is will happen only when the PC chamber pressure increases. And when chamber pressure increases, the gas phase reaction will be more predominant, and keep in mind that degradation rate also increases when the particle size decreases, and when particle size decreases, this X star, that is the stand up distance, also decreases. So, that regression rate will increase. So, we have looked at a very simple model and for the regression rate or the burning rate, and this can be utilized to at least predict very in a crude way. And next lecture we will be looking at example how to determine the burning rate using this expression. Thank you very much.